Welcome to my Commodore 64 Games memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Spy Hunter by Bally Midway, or is it Bally Midway? I'm not entirely sure. If you know, then please do add a comment in the comment section below telling me which one you think it is. I'm going by the French pronunciation of Bally, so it's Bally Midway for me. Anyway, so 1983 by Bally Midway and Sega. Sega seems to have been credited for the Commodore 64 version. I had the tape version back in the day, but I really became first aware of this game when I saw it in the arcade. Now, when I saw it in the arcade, I was actually playing the upright version at a campsite many years ago. I must have been about 10 at the time, or maybe a little bit younger, but I saw the upright version being repaired, so it was just a great big PCB, or maybe a couple of PCBs that the repair person was working on at the time, and it was just a whole bunch of chips and capacitors and resistors and stuff like that. Of course, being so young, I had no idea how it all worked, but the arcade cabinet was nicely fixed. Anyway, so this Commodore 64 version is actually, for 1983, it's a really excellent conversion. It's actually really quite close to the arcade, given the graphical constraints, because the arcade version has at least, two independent playfields. It has the characters for the score and everything, but it also has the background playfield, and it also has an independent playfield for the sprites. So, the Commodore 64 is already at a slight disadvantage because it doesn't have those independent playfields. But looking at the Commodore 64 version, we can see that it has nice, almost full screen scrolling. It doesn't have overlaid score or anything like that, but it does have the score at the bottom of the screen in a nice little separate score panel right down at the bottom, which is one character tall. The game actually needs, or can use, two joysticks. It can use the second fire button on the other joystick to fire the alternative, or to activate the alternative weaponry, which on the car is usually like an oil trail, or it's a smoke screen. So the objective of this game is to drive along, and pretty much as fast as you can, shooting the enemy cars, avoiding the civilian cars, which you don't get any score for, and actually I think if you shoot them, you stop accumulating the score. And you have to try and avoid getting impaled by the cars with spikes on their wheels, and you have to try and avoid the helicopter, and you just basically have to try and get as far along as possible, accumulating score. And then that's basically it. Oh, occasionally the truck that comes along and drops you off can come back, or there can be a different truck coming along which will upgrade your weapons and give you the second weapon, or it will give you a missile or something like that. So you can then take out the helicopter and other cars a lot more easily. So I had the tape version of this back in the day, and I was, very happy with this. I would play this for quite some time. I think actually it's technically pretty good. The game has a nice little attract sequence as well, so if you leave the game, it will loop around an attract sequence, which is actually very similar to the arcade. It will display the logo, it will then scroll on the level, and it will self-play the level. The music is okay, it's not too bad. It's not exactly the same, and there are some note differences, compositional differences, if you like, with compared to the arcade version. But, generally speaking, it's not too bad. And the sound effects are a little bit basic, but I suppose at the time, 1983, as I say, it's pretty good. It stands up pretty well as an arcade conversion, as arcade conversions go. When I was very young, my 10-year-old self used to imagine that the roads that peeled off to the left or to the right, or the river sections that come on, they would have some kind of like secret area where you could go off and explore if there was some kind of special condition reached in the game. Of course, I don't think it actually has that in the game, but this was my 10-year-old imagination running a bit wild at the time. Here comes the weapon upgrade truck. And now the screen scroll stops. Of course, the truck comes down and lets out my car, but with upgraded weaponry. In this case, it's an oil slick, so it goes along with the smoke screen. Now that was lucky. The bridge is not out this time, and there was a small little road off to the left where you could go into the boathouse. It wasn't needed this time around, but sometimes there will be a message on the screen that scrolls down with the road, I think it is. There we go. Bridge out, detour on left. So you have to go and take the left smaller road, and then it peels off to the left and it goes to the boathouse, and then your car changes into a boat. Am I going to get it this time? Yes, there we go. I didn't miss it this time. And there I am. I've got a boat now. I don't know how the boat has got an oil slick and a smoke screen on the water, but okay, fine, no problem. There's the road, it goes peeling off to the right, and now the river comes along, and instead of shooting the cars, you shoot the boats. To be honest, the sprites look a little bit chunky, but they're not too bad, I suppose. To be honest, I think the score panel, instead of using characters, could have used some overlaid sprites. You could have had the score at the top of the screen and the upgraded weaponry as sprites down at the bottom of the screen. You could have done this quite easily, I think, probably without needing any kind of special multiplexing or anything else, but okay. Using characters down at the bottom of the screen, it looks like characters. The split actually is quite good. If you notice, the split it doesn't have that usual 4, 6 or 8 pixel black gap. There is no black gap at all. It goes straight from the game display to the last line, which is characters, which is pretty cool actually for a game for 1983. It's actually quite unusual. I mean, okay, so what looks like the background grey screen colour wobbles around a bit when it transitions to the black background colour. As you can see, when the screen scrolls, it bounces up and down, and that's due pretty much to the VIC having a bad line at that particular point in time based on the vertical scroll. So here's the title screen scrolling on, you can see 1983 Bally Midway. So Sega, I think, might have done the Commodore 64 conversion of this or something. I really don't know. I don't know why Sega would have been credited for this otherwise. So here you can see the computer is self-playing a demonstration game. This is the title screen loop around attract mode sequence, basically like the arcade. It seems to be shooting everything and moving around quite erratically. There you go, see game over. The attract mode sequence is actually a lot shorter than the full game. So the screen is actually a little bit narrower because in the arcade the screen, I think, was actually vertically oriented, so it was a lot taller than it was wider. Because the screen is scrolling vertically, you want to have a nice lot of warning of what is coming up in the level. Anyway, so let's have a look at the tape version. And we can see here that the tape version seems to be loading stuff into the tape buffer as usual, but then it loads stuff into 0800 in hex, which is 2048 in decimal, which is the starter basic. As you can see, it's actually not an auto-booting tape loader, it's got a sys 2061. If we have a look at the code, we can see it's just doing a quite standard start up, it's not really doing anything special. It's jumping straight into 3E5, which of course is jumping into some code which was loaded into the tape buffer. There doesn't seem to be any kind of like protection stuff or much protection stuff. Maybe there is a little bit of obfuscation coming along, which we'll try and find later on. But this is, you know, quite an early Novaload. It doesn't even auto boot, so we can see a JSR to E000, which is interesting. It seems to be after it's loaded a whole bunch of stuff. We can see a restore for the, I think that's standard, pretty much. Well, actually, it's restoring the RAM-ROM configuration into location 1, which you would normally expect. Here we go. So there we go. It's actually setting up, I think, the IRQ there to do the loading. It's loading into E000 by the looks of that. There we go. Now we're going to get code in E000. That is, there we go. That looks like code. So there we have the JSR to FF84, followed by an RTS. FF84 is restore IO. Let's just double check. FF84 is initialize IO devices. Yes, so basically restore IO. Followed by an RTS. I don't think that RTS is going to stay as an RTS, or maybe it's going to push something onto the stack as part of the new loader code, which has been loaded at E000. So we'll have a little look at E000, and it's jumping straight to E008, which first of all does a screen clear of the Novaload message. It then, let's have a little look inside here, does stuff, which doesn't seem to have anything on screen per se. E071 seems to be getting data 1 byte at a time, which is interesting. So we can see here that it's storing data into the screen from whatever is it, E071. E071 just seems to be, yeah, it seems to be a simple load accumulator indexed with X, increment X. So it's just loading stuff from higher up in memory and then bunging it down into elsewhere. Now this is the loading, so we can see here that it's actually loading data. We want to double check what is actually doing the data load. So if we let's put a watch on store of say 7F00, and then if we have a look here, we can see when it starts trying to load up to 7F00 hex, and then we expect the store to, here we go, and we can see that if we look a little bit, there we are, that's as expected. So we're storing indirected with A5, indexed with Y, and the accumulator is coming in as part of, looks like it's in IRQ mode. Looks like there is just an IRQ load going on here. Nothing special. Oh look, what was an RTS after the FF84 has now turned into a jump. Okay, well that's not entirely, you know, unexpected. It was either going to be self-modifying that code, or it was going to be doing, you know, like I said, a push onto the stack. So I'm glad to see that it's doing a self-modify of that code in memory. Let's just put a watch on that memory address for store and see what updates that memory address. That would be a good idea. So we want a watch on the store for 3F5. This is during the Novaload, where it's loading all of that extra loader code up in memory. So there we go. Look, see, it's updating the, oh, so it's doing an E281. So JSR to E281. E281 seems to be doing, you know, another incremented load, this time absolute, and it's just returning it in the accumulator. So it's basically pulling a whole bunch of extra stuff higher up in memory and then deciding on what it wants to do with those bytes coming from higher up in memory, sometimes one at a time and sometimes in sequence like this. So there we go. So kind of like an optimized memory copy into lots of different places, basically. Funny that you can see, look, the last thing it does is it does an RTS. Okay. So let's let all of the game code load. So there was a little bit of obfuscation there, but to be honest, not terribly difficult to figure out. There we go. We don't care about the initialize IO up in the kernel. And there we go, it goes into the game. Now, the initialization for the game code was actually doing quite a lot, way lower down in memory. So we're going to have a slightly deeper look at that initialization to see what it's doing. I noticed that when the game code was running, the scroll was actually running quite a lot of unrolled loop code. So when we talk about unrolled loops in assembly language, it's basically all of the instructions without any kind of like indexing, usually to remove the need of having longer to execute indexing instructions. It unrolls the code itself and does a whole bunch of load store for, you know, the area of the screen that you want to move around. It's a lot faster to do it like that, but it uses a lot more memory. So that unrolled loop code was actually stored way down in memory. So when the game finishes loading, there's a whole bunch of extra uninitialized memory. There's some memory up at F000 in hex onwards, which seems to be, I thought when I had a look at it, it looked like it was level data. And then there's a whole bunch of sprites up in the second bank along with character sets, which when the game loads, actually that memory is not really initialized. So I noticed that the game code seemed to be doing quite a lot of what looks like decompression, some rudimentary decompression at the very least. So there's initially quite a lot of memory moving around and a lot of memory calculations. This does quite a bit of memory moving around. This was moving memory from D0 to 00 to E000 in hex. And then it's jumping indirected to 8002 in hex. That's interesting. That tells me that there might be some... And there we are. We can instantly see that there is a CBM80 cartridge or basically kernel cartridge hook right there. So we can see that it's using that. So if you try and reset this game, it won't let you go back to basic. You have to turn the computer off and turn the computer back on again. So this first JSR seems to be doing a whole bunch of initialization. It's actually clearing pretty much the whole of 0 page. Now watch the memory view window when we run this, because this seems to be doing, at first glance, setting up a whole bunch of perhaps pointers, and then doing a whole bunch of, then doing some kind of either decompression or optimized memory copy. Let's have a look what it's doing. It's step in, we can see here. Okay, this seems to be doing the pre-calculation for the unrolled loop code. Or the unrolled code. So the unrolled code consists of load store, with incrementing memory addresses for the two character screen banks that we'd used during the scroll. Makes the full screen scroll nice and fast and optimized, which allows more time for the game logic later on. So if we go back to the ROM characters and we look at high up in memory, at the moment it contains the tape loader screen and then a load of uninitialized memory. If we let this code run, watch the memory view window up at the top and also watch the text screen window, and you can see that it will do a lot of updates. Once we step out of this, let's just see what it's doing. It's just doing a whole bunch of arithmetic with the values that were passed in. The values that were passed in seem to be configuration values to configure this code to tell it how to generate the machine code that we want to see for when we're scrolling the screen. So if we so pay close attention to these memory views and debug text screen views, we will step up. Bing. You can see that the whole chunk of memory up at the start of memory was initialized, and we can see that memory now contains, if we disassemble it, a whole bunch of load store, and it does that for several pages of data. This is the loader screen data. There we go. It was then calculating what looks like map data, and it looked like it was doing several read and write passes over this. So it looked like it was using some code to pre-calculate or generate, or maybe decompress from seed data or compressed data in memory, the level or the game level map which scrolls around. Now, the game map itself contains various horizontal sections which are bolted together to make it a more continuous map. So the road moves left, the road moves right, it splits, the road changes from green to desert type and then to ice, and there's water, bridge sections and stuff like that. So all of that map data looks like, when I was looking through this earlier on, we'll come to that a bit later on, it looks like it's calculated by several passes or decompressed by several passes into that memory, and there's two memory chunks. The first memory chunk is just after the unrolled loop code, and then the second memory chunk was way up in memory at F000 onwards. And when the game is scrolling, it's copying from both areas depending on if it's water or bridge or desert or the grass tree area, for example. Here, the code that was just running there, you saw that, right? The sprites were decompressed into memory, and also the character data. So now, if you have a look, the background level data there now contains the character data which matches up with it, and it looks like horizontal strips. Now, the screen is narrower, so these horizontal strips show this kind of like diagonal effect because the screens that are being displayed here are 40 characters wide, whereas the game level is something like 34 or 36 characters wide. I'm just guessing, but it looks like it's about that kind of offset, maybe even narrower. So here you can see the two screens, the on-screen and off-screen buffers, which are being scrolled a character at a time, but the vertical scrolling is obviously pixel level vertical scrolling because it looks a lot smoother. You can see here that the code is running alternate copies, and it's running through the alternate unrolled loops. So it does one and then the other for the two different screens, and it's alternating there up in the memory. The very top of the memory view, which is in blue here, indicate executing code. When the title screen comes and scrolls in and scrolls off, you can see it's executing the blue code way up at the top of memory, the unrolled loop. So, not a great surprise that the title screen scrolling on and scrolling off is using exactly the same code and pretty much the same game logic for transitioning to the level itself. And there we go, if we have a breakpoint there, we can see when the screen scrolls, the code is hit. So we know that what that code is doing. And there are the two screens with the matching character set data, which matches up with the load store addresses being used for the screen memory copy, which is what you would normally expect. There doesn't seem to be any extra sprites in memory. Everything for the graphics seems to be held in the bank at 4000 in hex. So you can see here that actually the score panel down at the bottom is being updated with a different character set, not at 7000 in hex, but at 6800 in hex, 6800 in hex. And interestingly, the score panel seems to be, in the screen data, seems to be updated on 2 lines identically, whereas we're only seeing 1 line in the score panel. Now, I know why this is. It's because the transition from the screen, from the scrolling screen up at the top, is using 1 pixel row. Now, when the VIC is told to do that at certain points, depending on the vertical pixel scroll, it will get a bit confused about which line, which character line of the screen it wants to render. So, interestingly, very cleverly, the programmers decided, well, they're going to have a single character row, and you can see here, if I put some background, if I put some graphics only on 1 character row, you can see that the graphics in the score panel display, when the screen scrolls in pixels, it alternates between which character row it's displaying. So you get the flickering characters down here, proving that we're rendering from 1 character row or the other, depending on the vertical pixel scroll. And this is to do with the bad line calculation and how the VIC deals with transitioning from the vertical pixel scroll value to a stationary pixel scroll value. And so this dual character row update avoids the usual kind of like bug where the VIC doesn't quite know which character line it wants to render from. Very clever, because it only really kind of like works, generally speaking, if you can get away with updating a single character row for the score panel. It's controllable, where you can work out what you're going to be doing, and you could update the entire score panel if you wanted to have a score panel which is 2 or 3 or 4 or 5 character rows high. You could do that, but it would be quite expensive in terms of updating the entire data in terms of screen memory. You could have 2 different screen banks, of course, one with the score panel in a different vertical position, but then you'd be wasting almost an entire screen bank to have that kind of data there. Another way of doing it is, of course, to have the wider, say for example 6 or 8, usually 8 to be honest, blank empty lines where you can stabilize the VIC properly so that it will always be rendering a consistent number of rows for your score panel. And that's a lot easier, but it wastes 8 pixels of blank display area that you could use for the game. And I guess the programmers in this version wanted to have as much vertical display area as they could get. So if I was doing this, I would probably use sprites as an overlay for the score panel. I wouldn't use characters, and I'd scroll the whole screen. But that was their design decision, and it's perfectly valid to do this kind of thing too. It's only 8 pixels. What you could have done actually is that you could have opened the bottom borders and top borders, vertical borders, and you could have actually put all of that score panel data in there. I would have done that too, probably. Although this probably came out as an American release first of all, and the NTSC American machines they have a lot less raster time, they have a lot less vertical border space, so as we saw with the Whizball, only some parts of the vertical border can be used effectively. I mean, there's not that much space there for the sprites in terms of the borders. So that was an interesting find. That's a really interesting, quite a mature, for its time, back in 1983, quite a mature way of dealing with the screen scroll. So here we can see a bunch of sequential reads when it's scrolling this tree green part of the level, and I think these reads are at F00. Let's restore the character set back to what it should be. There we go, and we look at the screens at F00, and I'm pretty sure it's reading spans of data sequentially as it goes along, and it's doing that to render the trees and render the road. Yeah, definitely that kind of look to it, right? Oh, actually, the map data is at E800 as well in the previous bank of 4 screens, so that's cool. We will use the attract mode sequence here to reliably find what memory address is reading here. It looks like it's the same kind of one, right? So I've got an idea. First of all, I just want to have a little look at the split, which is updating the screen and background color from grey to black. There we are, it's updating it with black here. It seems to be that it's inside an interrupt. Yes, it's inside an interrupt. You can see the code going from what is the main line, which is non-interrupt code, to the interrupt code itself, doing a clear decimal, pushing all of the registers onto the stack, doing a whole bunch of looks like timing. Yep, timing to time the change for the screen vertical scroll and the character set and the actual screen bank that it wants to render, and of course the screen and border color as well. There we go. Just double confirming that this is the bank for the score. Yes, that was it, right? So these are the sprite pointers that are set during the score panel. It's all 95 in hex. So let's change them to point to 0, which should be the first sprite in the bank, which is a bunch of strange looking data. Now, and you can see here that the sprites, when they go over the score panel, they are now showing up over the score panel with what looks like strange corrupted sprite data, which is what we would normally expect. There you go, you see this car comes on and then it looks a bit strange. So we know now that it's relying on the trick of setting up empty sprite definitions in the rendered screen bank to basically chop off the bottom of the sprites with transparent data for the point in the screen where we don't want to see any sprites over the score panel, which is the quickest and most effective way of chopping off the sprites at a particular point to avoid them being seen over the score panel. It's a nice thing to do. It's free because it happens when you change the rendered screen bank. You don't have to do anything special. You don't have to do any extra stores. So it's like a free effect, if you like. It's a side effect of the screen bank that you're displaying. Because that's what the VIC does. The VIC gets the 8 sprite pointers for what sprite data to render from the 8 bytes at the end of the currently rendered screen bank. And it does that all the time. Every scan line, basically. So we can see the level data starting here, up at the beginning of memory just after the unrolled loop code. And we can see what looks like more, well, this is the text data for the various different game messages. And then we've got extra level data starting here at what looks like E800 in hex, all the way up to F800 in hex, consistently reading data from that area of memory. So what we can do is that we can fill the what looks like level data with let's choose a good character that we're going to render with. There we go. Now when the screen scrolls, if the screen scrolls, there we go, the screen scrolls and it's making the game render the rubbish level data. So we know that that is basically, it's confirmed to be the map level data area. At least when it's doing the attract mode and when it's rendering those green areas with the trees and stuff like that. So let's just, there we go, see I've changed the character and you can see that it's definitely rendering a different character now. So yeah, interesting. And the game logic is now confused because it scrolled on what it thought should be a nice working level, but there wasn't any area where the truck could come on and put the car down, so now it's getting really confused and it's not working, and the game logic seems to handle it, and it seems to reset the level and then finish. Okay, well, there we go. So the game logic seemed to handle that weird data problem. So I noticed earlier on that this US Gold loading screen seemed to have an interesting artifact. Oh, it doesn't like the tape being stopped. It reset the computer. So let's try that again. What I'm really interested in is the actual US Gold screen coming up. So when I was looking through the game, when I was looking through the code earlier on, I saw what looked like some scrolling of the character screen data, but there didn't seem to be any scrolling message. Now usually this screen has a scrolling message, so let's put, yeah, you see there's a little split which is doing a pixel level scroll horizontally, and we can see that when I add the characters using the screen editor to the screen memory. It's actually scrolling along the extra character data that I put in. So yeah, there doesn't seem to be a message in this version of the loader, but there is still all of the code there to handle the scrolling screen message. Isn't that funny? And you can see that the far right character is actually not being scrolled onto the screen at all, so there's a little bug in the screen scroll there. But I don't think there's an actual message or anything. I didn't see any extra message that would have been added. So there we have it. So they didn't remove all of the code, they just blanked out the message. Or didn't even store it into the screen by the looks of it. The character, the tape block display seems to get very confused if you put the wrong characters in there, as opposed to the 0 to 9 characters. It doesn't count down properly, but that's okay. The game still starts because the internal counter, there's obviously an internal counter for the number of blocks, or actually the game code starts when the expected end address has been reached for the game load. So let's have a little look at the original disk image for the disk version of this. Now, I did not have the disk version at the time. This was this was released way before I even had the disk drive. I just had a tape drive for so long with my Commodore 64. So we can see here that there's, Spy Hunter, Loader, Tap, Pick, Sprite, Tapper. Tapper is a different game. I don't know why this original disk image would have Tapper related files, which is really odd. And actually, so we've got Spy Hunter. Now, Spy Hunter is the first file which would tend to be loaded first when you load the first file on the disk. It's 1 block long, which tells me that it's probably very simple code which loads a bunch of extra files, or it's auto booting loader code. Let's load loader. There's nothing there, but where did it load to? What memory address did it load to? Let's have a quick little look. Oh yeah, look, see, C2 BC is the ending address for the load, but we'll guess, because it's a block long, that it started loading. Actually, it was 3 blocks long, wasn't it, or something like that for that loader file? So we'll guess that it's C000. Oh, look. Illegally copying a disk is a federal offence. Well, yay. We can see here it's loading Tapper, loading Sprite, Tap Pick, Sprite data, loading Tapper. So yeah, interesting. Tapper is on the disk which contains Spy Hunter. Weird. Okay, well, we'll have a look at Tapper at some other time. This is a Spy Hunter video, so let's get rid of that. What are the other files on this disk then? I'm really interested to see what these other files are on the disk now. We have the Spy Hunter loader, which just loads a whole bunch of memory, and it seems to be loading a whole bunch of memory at the tape loaded data, and it seems to be doing the same kind of code generation and or depack of the map data as before. So it looks like, although I'm not going to do a binary compare because it's a bit tedious to be honest, it looks like the disk version of Spy Hunter is the same as the tape version. Doesn't look like there's anything extra special or change there. I'm more interested in what these other files are, so let's have a look at Spy. I'm not going to look at Spy. TapPick. Well, we know that TapPick was being loaded. It's loading a whole bunch of data up at what looks like 400 in hex, maybe a bit further on. Wrong way. There we go. Yep. Looks like a whole bunch of initialized data. So let's see. Let's get the old bitmap viewer out and have a quick little look. Oh yeah, there we go. There's the Tapper bitmap for the loading screen. Okay, that's fine. Let's load. Well, there's a different version. This is accredited to Sega in 1984, and it's just got two files. It's got Spy Loader, and then it's got the Spy, and when it seems to be loading at 7000 in hex onwards, and it seems to be loading exactly the same version as before. It's got a date stamp and it's got a version number. Interesting. It's got the CBM 80 stuff. It's got pretty much exactly the same kind of thing as before. It seems to have got stuck, which is a bit odd. Why did it get stuck? Unsure. Let's just go. It's not happy. Because of the cartridge auto start code vector claiming thing at CBM 8000 in hex, it's not resetting. So let's go. Anyway, so let's go back and have a look. What is it doing? Yeah, it's really not happy at the moment, is it? That's really quite strange. I wonder why that is. Anyway, so let's go back and have a look at the other disk, which did contain. Let's load S1, and again, there's nothing loaded, but if we have a look at where it was loading, oh look, it's loaded some data at C000 in hex. Let's have a quick C400 in hex, sorry. Oh look, it's doing a whole bunch of loads. Beachhead? Why on earth is Beachhead on the Spy Hunter disk? Maybe it's a compilation disk, but if it was a compilation disk, I would have expected to have seen a nice little boot menu or something. Not just a whole bunch of files stuffed on the disk in really weird order. Is it the full Beachhead? Let's start a game. Yeah. Well, it looks like it is. Well, that's strange. Okay. Well, yeah, this is the Spy Hunter video, not a Beachhead video, so let's get rid of that. It's loading a whole bunch of code up at this time. Oh, look, 2000 in hex. What is it, 8192 in decimal? Yeah, look, see, there's a whole bunch of code here. Oops. Let's disassemble that again. There we go. There's a whole bunch of code here. Setting up some 0-page pointers, doing a whole bunch. Let's just, oh, well, if we call it, then it does a whole bunch of memory copies. And this compressed data, which looks a little bit spritey, but it's not quite spritey. Yeah, this is compressed data, which is loaded from the disk. We call it, watch the memory view. It's reading from that and then storing way higher up in memory. Oh, and look, there's a whole bunch of extra sprite data. The decompressed sprites are in the second bank. and it actually runs over and over again. Interesting. So we can fill it, and then we can run it, and there we go. Wow, okay, cool. And they're flipped sprites there. It does look like it's automatically flipping the sprites, maybe. Or maybe it's an artifact of the decompression. Oh well, interesting. What a surprise, yes. So I guess the programmer for Tapper decided that they wanted to save some disk loading time by having compressed, or at least some compressed data. So there we have it. That was Spy Hunter with a little bit of a technical deep dive into this really quite small, but one would say almost perfectly formed arcade game conversion. If you like these kind of C64 Games Retro Memories videos, then please do consider liking or subscribing to this channel or sending me a comment in the comment section below. Thank you very much for watching and have a great day wherever you are.